point, but it was useful in that I had some severe technological limitations. I went to do a longer video and it froze up trying to upload, so I cut it short, redid it, and did a shorter one. Fortunately, I will be doing a longer one from here tomorrow, so that Fridays will be a full lecture. But I want to review a couple things just from the lecture. So if I have a reaction, the general overall reaction, I can write something called an equilibrium constant for that, and I'm not going to go through the difference between that and the rate constant. However, the equilibrium constant is a capital K. How do you know it's a capital K? Because I tell you if you have to ask that. It's an equilibrium constant. You're going to have to use context. And a rate constant is a lowercase k. A equilibrium constant is an uppercase K. This is probably the most useful constant in chemistry, possibly eclipsed by the ideal gas constant, but this is the one that you will see more than anything else that will be used. Now, K may or may not have a subscript to it. K is a generic equilibrium constant. I can put a Kc in it, indicating in equilibrium concentration, equilibrium by concentration. Kp, equilibrium by pressure, that's generally used for gases. I can have Ka, which is an equilibrium constant involving sorry, now it's big stream of cold air coming right through there. So I thought maybe if I shut that, that'll help. I'll open it up later. Keq, generic equilibrium constant. Ka, acid equilibrium constant. Kb, base equilibrium constant. There's all kinds. You'll see a lot of them. Kf is a formation constant, but they're all equilibrium constants. And they're all based on a generic thing where we're going to take the products and their concentration or some measure of that. What do the brackets tell us? It tells us not only concentration, but it tells us the units as well. So it gives us a concentration in molarity, okay? And this is our equilibrium constant. This is based on something called the law of mass action. Now, what's a law? Something that we always see to be true. We have never seen an exception to the law of mass action, but we don't have any proof of it. Well, there's lots of people who think they have proof of it, but it's still a law, okay? So this is a basic assumption, and it has always held true in everything we've done. So we're going to use that. Okay. Now, we're going to look at how we can calculate values with equilibrium constants. And I will go through a little bit more of some details of manipulating equilibrium constants. And I think I talked about the magnitude of it and the reaction quotient. But what I want to look at is a method of calculating values from equilibrium constants. So we're going to start with this equation here. Okay, H2 plus I2 gives us 2HI. And I know that might be too high for all of you. Let's see if I can cut glare down. It's pretty bad when I see glare on my face shield, so it's having trouble reading it. Okay, so at a particular temperature, the equilibrium constant for this is 50.5. Okay, so what does this tell us about this reaction? It tells us that in general, it's a little bit product favored. Now, its magnitude is only like to the power of 10. Okay, it's less than 100, so it's not super concentrated on the product side. We can see equilibrium constants that are as large as 10 to the 20th or as small as 10 to the negative 37th. Those are not uncommon. Okay. So product favored, if it's between 0.1 and 100, even though it's product or reactant favored, you will expect to see significant concentrations of both of them. So we're going to take a look at how to calculate this. Okay. And we're going to use something called an ICE table, which is kind of appropriate with our weather. Okay, now what does ICE table stand for? I-C-E. I stands for the initial concentration. C stands for the change that is going to occur. And E stands for the equilibrium conditions. Now, there is another chemist that likes to put a R by the reaction, and he calls it a Rice table, just because he went to Rice University. I mean, that's why. So you might see it as a Rice table by somebody else, but it's an ICE table, and it's commonly referred to as that. Or, if you want to, you can call it an ice box. Okay, and I'm going to start with a simple calculation here. We're going to assume that at the beginning, that H2 and I2 have an initial concentration of 0.1 molar, and the HI concentration is 0. So when I do this, how am I going to determine the equilibrium concentration of each of the three substances? Well, I'm going to start by indicating the initial concentration. Now, these two are easy because they're given. Now, again, it's molarity unless you say otherwise, so I'm going to leave the units out of here just for clarity's sake. And what's my initial concentration of the HI? 0, right? And I know some of you are saying that's too high. Okay. All right. The next step is really important. Okay. And I am going to ask you how much of that H2 is going to react. What do you think, Asher? How much is going to react? Okay, he doesn't know. Emily? Brandon? You don't know. And you both got the right answer. However, algebraically, how do we say I don't know? X. Exactly. Now, is it going to go up or is it going to go down? Well, I know with this concentration of 0, I'll show you how to calculate it if it's not 0. But if I have 0 for my entire product side, I can't have an increase in my reactants. I can only have a decrease. Now, if this is minus X, because this is a 1-to-1 ratio, this is also going to be minus X. And this is a 2 as our coefficient. I have to take that into account. And this is going to increase by 2X. See how hard this isn't? Where do I get the numbers in front? The coefficients. Okay. How do I determine everything on one side is negative, everything on the other side is positive? And so far, we just know if it's 0, it has to be a positive one. It has to increase. We'll look at some more with that. Now, in this case, 0.1 minus X, 0.1 minus X, and 2X. If I add the initial and the change, I get the equilibrium value. All I've done is added the two lines together. Now, in order to work this, I really should write my equilibrium constant. So in your work there, I want you to write what K is equal to, and then I'll put it up here. I want you to get a little practice at it first before I do it. Okay, so products, the power of their coefficient over the reactant to the power of their coefficients, in which case for the reactants, they're both 1. So this is my equilibrium expression. And I know that K is equal to 50.5, and that's equal to my 2x squared over 0.1 minus x for this one, and this is 0.1 minus x. Are you okay if I put a square there instead of writing it twice? Now, if we wanted to, we could expand this out and solve it using a quadratic equation. Sometimes we have to use the quadratic equation, but not this time. Is there another way we could simplify it? Well, notice that both of these are squared. So what if I square rootify it? I know I made that word up. Okay, but I'm going to square rootify it. Take the square root of both sides. And this is, I think, what, 7.2? Somebody with a calculator, square root of 50.5. 7.1. Okay, so now I have a single variable. I'm going to multiply both sides by 0.1 minus x. Add 0.71 to both, 7.1 to both sides. And whatever 0.71 over 9.1 is. So that's 0.078. Now this is not, however, any of our equilibrium concentrations. This is our value of x. If I want the equilibrium concentration, I'm going to take 0.1 minus x, which gives me and 0.078 times 2. So I have my equilibrium concentrations of all three values. Now, one of the things that we will commonly do is check our work. So let's put these values back in here. So if this is 0.156 squared over 0.022 squared, what do I get? That's not going to give us exactly the 50.5. Why? Because I only gave you two significant figures. But it should give us pretty close to that. Okay? Relatively simple calculations many times. Look for a way to simplify it as much as possible. Okay? We'll look at other ways to simplify things here in a bit. But for the moment, let's use the same scenario. Oh, you should still have the equilibrium constant written down. But let's come up with a different scenario.